Hello everyone, today we will presenting on stereochemistry in organic molecules that covers concepts like chirality, enantiomers, diastereomers and racemic mixtures. So this topic is essential in understanding how molecules are arranged in three-dimensional space and how this affects their chemical, physical and biological properties. We will explore key concepts, real-world applications and how stereochemistry plays a crucial role in biological, pharmaceuticals and biological systems. So, what is stereochemistry in general? It's a branch of chemistry that studies the three-dimensional spatial arrangement of atoms in molecules. And many biological molecules like proteins, DNA, enzymes, and so on, they are stereospecific, meaning they only interact with certain stereoisomers. And here we have stereochemistry is not just a theoretical concept. It has profound implications in real life. One of the most tragic examples of its importance is the thalidomide tragedy that occurred in the 1950s. So, next. In organic chemistry, many molecules have tetrahedral structures due to sp3 hybridization of carbon. For example, a carbon atom attached to 4 different groups forms a chiral center, creating two mirror image molecules called enantiomers.
So, what is stereoisomers? Stereoisomers are isomers that have the same molecular formula but the different spatial arrangements of their atoms. They can be divided into 2 types, enantiomers and diastereomers. Enantiomers are isomers that are not superimposable mirror images of each other, and they have the same physical properties. For example, the D and the L lactic acids. So the next is diastereomers. They are isomers that not have the mirror images of their image. So, for example, the cis-trans isomers in alkanes and the cyclic compounds. So the next is optical activity. Optical activity is the ability of a chiral compound to enter the plane polarized light. Polarizer enters the light, allowing only vibrations in one plane. So optical activity can be divided into 2 types: the extrarotatory and the levorotatory. The extrarotatory, if the compound is rotated into the right and clockwise, it's called extrarotatory, and we can name the compounds like D-lactose, D-lactic acid, and the next type is levorotatory. Levorotatory if the compound is rotated to the left side anti-clockwise, and we can name these compounds like L-lactic acids and L-lactose, like that. So the optical rotation is detected by the polarimeter. Optical rotation is the angle of a plane of rotation. So polarimeter determine if the compound is dextrorotatory or levorotatory. So the next is about chirality. Chiral compounds are compounds that have non-superimposed images of each other. So, for example, our hands, our left hand are superimposable to our left hand. So, compounds have chiral centers, and for example, here have image of the compound that have chiral compound with 2 chiral centers and with 3 chiral centers, and it can be more or less. So that's all. The next part will be explained by Lagyl.
So now let's talk about enantiomers. They are superimposable mirrors of each other. So you can imagine your hands. They're the mirrors of each other, but you cannot really align them so that they're the same. This is exactly how enantiomers behave in organic chemistry. what makes enantiomers is that they have chiral centers. Those are usually the central carbon atom that is bonded to 4 different groups. The spatial arrangement of those 4 groups determine the handedness of the enantiomer, which is chirality. Because of that, because they have the same molecular structure and also the same connectiveness, they have the same physical and chemical properties, except for one key aspect, which is how they behave, how they interact with polarized light. One enantiomers, they rotate the light, polarized light, clockwise, which is called dextrorotatory, and the other rotate it counterclockwise, which is levorotatory. Let's move on to diastereomers. They are not mirror images of each other, and also they are not superimposable. This means that they can have different spatial arrangements, and unlike enantiomers, they don't exhibit the same symmetry. Also, another difference is that while enantiomers differ only in optical activity, diastereomers can behave completely differently in reactions. Also, can have different physical and chemical properties, such as melting points, boiling points, solubilities, or even reactivity. And moreover, diastereomers are achiral, or they can have multiple chiral centers. For instance, D-glucose and D-galactose are diastereomers of each other, and they differ only in one chiral center, but can have completely different biological properties and reactivities. Now finally, let's talk about racemic mixtures. Racemic mixtures are the combinations of 2 enantiomers. The first is dextrorotatory, the next is levorotatory. Since they rotate plane polarized light in opposite directions with the same exact magnitude, the effects cancel out. And it makes the overall mixture optically inactive. Those racemic mixtures often occur during the chemical reactions where chiral centers are formed with no real preference for one enantiomer over the other. Most drugs and also natural compounds occur to be racemic mixtures where one enantiomer is biologically active and the other is not. For example, the famous example is the ibuprofen, where one enantiomer is a painkiller while the other is biologically inactive. Lastly, one of the major issues is that scientists and doctors have to separate those enantiomers in the mixtures, and for that reason they use resolution techniques, which are really complicated and and pose as an issue for pharmaceuticals.
Representation of 3-dimensional structures. In stereochemistry, it's very crucial to determine the structure of molecule in 3 dimensions. So we commonly use dash wedge notation, for example, and where solid wedge is represented toward us. Also, we have dash wedge that's represented behind, and the straight line that's represented of plane of the paper. So in this case, we can clearly visualize their structure. The next is feature projections that can be used for amino acids, sugars, and by the carbon placed at the top, and the horizontal bonds represented toward us, and the vertical represented like behind of us. So in this structure, we don't need 3D models. That's why it's also easy to identify their structure. The next is Newman projection. In Newman projection, it's very crucial to visualize how can they rotate. So in this case, we need carbon-carbon bonds, and also we need atoms and ropes to be analyzed how they are located on the bonds. So in this case, we can confirm it by the Stereochemistry and eclipses to identify their reactivity and the stability. And the last one is Sauer's projection, using for single bonds to confirm their rotation. So the next is elements of symmetry. Elements of symmetry, we need to identify chiral and the achiral molecules. So chiral, it's like can be mirror imaged, but achiral cannot be. So how it works? So plane symmetry, when it's like divided our like molecule to pieces, can be image mirror. So we can call it achiral. The next is center of symmetry. Of the center of symmetry, in each like molecules or groups of atoms have their counterparts like opposites, and by them we can say it's achiral. And the last one is about alternating axis of symmetry. So it can be identified the rotation of it and how it can be unchanged. So in this case, if all like elements not in the molecule, so we can say it's chiral molecule. So chiral molecule is like we can call it also enantiomers, that uses for pharmacy to having from one compound two enantiomers that can be affected to our body differently.
So let's talk about the different ways of how we name molecules based on their 3D shape. So first one is DNL system. DNL system is based on how we compare our molecules to the DNL glyceraldehyde. Glyceraldehyde is a type of sugar. So if the molecule is more like D-glyceraldehyde, we call it D. If it's more like L-glyceraldehyde, we call it L. So it's mainly used for sugars and compounds with chiral centers, which means that every atom is arranged in the way that makes them not identical to their mirror image. So second one is erythroentria system. It means, it's like this system helps us to tell apart the diastereomers. It's molecules which have the like two chiral centers. So in a erythro form, the molecule in an erythro form, we know that the similar groups, they're arranged in the same side, on the same side, while in trio system, they're located on opposite directions. And the third one is really commonly used one, RNS system. It means RNS system. What is this? So it is based on Kahn-Ingold Prelog priority rules. So our groups which are attached to the chiral atoms, they are given the priorities by their according to their atomic numbers. So when we arrange them in order, if the arrangement moves in a clockwise, we call it R. If it's counterclockwise, we call it S. Is an application of stereochemistry, pharmaceutical. First, let's talk about the pharmaceutical one. Let's take the example, for example, thalidomide. The problem with this molecule is that it is made up of two mirror image molecules, like enantiomers. So the problem is that one type of this molecule is like, for example, thalidomide is really essential in pharmaceutical because it can treat our morning sickness, while the other part, like the mirrored one, it can cause severe burst effect. That's why it's really important on how we choose, in which type of molecule we use in a drugs. And the third is the second is biological molecules, amino acids and sugars. We know that in our body, the amino acids and sugars, they have specific 3D shapes. So like amino acids in our body and protein, they have L-formed shape. So if it switched to the D form, it will make molecules wouldn't work at all. So it's really essential to know about their arrangement. Let's talk about the polymer chemistry, toxicity in plastics. So, for example, if we want to make the plastic more rigid or strong, we need isotactic polymers, which are as you can see here, not random. If we're gonna make them more elastic, more elastic, we have to use like flexible. We have to use atactic form. So, in conclusion, of course, stereochemistry is really essential in understanding molecular interaction, and it plays a really crucial role, as I said before, pharmaceutical, biomolecules, and material science. So, also help in predicting chemical behavior and reactivity. Thank you.